Hi everyone, welcome to the fifth lesson in our fourth unit of Science 10. This one is about thermal energy transfer in the hydrosphere. In the last video we focused on the atmosphere. This time we're into the hydrosphere. So with hydrosphere, of course, you're guessing that we are working a lot with water. Part of this is going to be a bit of an understanding of the impact of water on various climates. And then we're going to look at some calculations involving water and energy. Specifically over here, you can see you're going to learn about specific heat capacity, which probably is pretty new. Quantity of thermal energy, the hydrologic cycle, and heat of fusion and vaporization. Most of those, to the best of my knowledge, should be pretty new to you guys. All right, let's get started. Now, thermal energy transfer in the hydrosphere. The hydrosphere transfers thermal energy in a similar way as in the atmosphere. Surface water is pushed by trade winds. Well, that makes sense. So you have to think in this case, we know that water holds energy, and we know that the surface of water will be pushed around by wind. That's pretty common. Deeper water travels by convection currents. Now remember in the last video or last lesson, we talked about convection currents, remember? Where we had, let's say, a heat source. That's my ugly heat source. And then remember, water, let's say water particles or air particles are right here. Now they are going to be heated. They are going to accept that energy. And as we said, they become less dense. And what happens is they rise up. And as they rise up, they actually lose their energy. So then they clump back together where they're cooler. Now when they're cooler, they fall back down as they lose energy. But then again, they get heated up again. So it's a continuous cycle. Now we focused on that in the atmosphere, and what we had stated is how there's kind of this flow of air from the equator to the poles. Just so happens that the same thing happens with water. So if I were to draw, let's say, well, I'm a pretty bad drawer, but let's say if you had like this is the Earth, and there's your equator, and that's terrible. But again, remember, water will be heated at the equator, and it'll move generally up to the poles. As it cools off, it will flow back down, and the cycle continues. So as it says right there, warmer waters near the equator are driven by convection currents towards the poles. Currents in the northern hemisphere circle clockwise, southern hemisphere counterclockwise. Unlike air currents, which do not circulate around something, water currents are distributed by continents. I think the main thing here to focus on is just make sure you understand how water is flowing right there. Okay, let's move along. That's something that you guys have talked about already. This is kind of interesting when I thought about this. It's from the textbook, and I thought it was really important to put in here. You have 3 Canadian cities. You have Vancouver, British Columbia, you have Lethbridge, Alberta, and Gander, Newfoundland. Now, it says here that these 3 cities are essentially at the exact same latitude. Another way of putting that is they are, give or take, the same distance away from the equator or north of the equator. Now, I'll continue on here. Because they are all the same distance from the equator, they are subject to the same air currents. So we might expect they all have the same average temperature. So you see, if you focus on the atmosphere, like we did in the last video, we can give or take say that the air flowing over these 3 cities should be give or take the same. Now, so if the air is the same, we would figure maybe their climate, their temperature is the same. But if you look at the table here, Vancouver, the average annual temperature is 10.1. The average temperature in January in winter is 3.3. In July, it's 17.5. But look at Lethbridge, look at Gander. If they're experiencing the same air, let's say, the same amount of energy in the air, well, why the heck are these temperatures so different? Well, you might have guessed it. It's going to be something to do with water. Okay, so we're acknowledging that the airflow, give or take, should be kind of equivalent, yet you can see the climates here, the temperatures are all over the place. So we have to understand why that is. This here just kind of recaps. Says Vancouver has the warmest annual average and the least monthly temperature variation. That makes sense. Gander has the coolest annual average, but also less variation. Lethbridge, in Lethbridge, the average annual temperature is between the other two, but sees the most variation. These three observations can all be explained by the presence or absence of a large body of water next to the city. So here you go. They're already were saying to you that the whole reason for this variation in temperature is going to be due to a large body of water. Now, in order to explain that, what we want to talk about is called specific heat capacity. So here you go. There is one important property of water that affects global energy transfer. Water has an unusually high specific heat capacity. Specific heat capacity refers to the ability of a substance to absorb thermal energy without changing temperature. The high specific heat capacity of water means that it absorbs much of the sun's radiant energy but stays at a constant temperature. So what I'm trying to say here is water has this ability to absorb a great deal of energy from the sun, or it could even be, let's pretend you had water on a stove. The point I'm trying to make to you here is, if you want to make the temperature of water increase, you have to supply a great deal of energy. Water has a very, very high specific heat capacity. So again, one more time. Specific heat capacity refers to the ability of a substance to absorb thermal energy without changing temperature. I want you to think of that now. Water requires a great deal of energy to be absorbed if you want it to increase in temperature. Now, we're going to tie this back around here to this whole thing about the three cities. So just keep in mind, water has this ability to if you wanted to raise the temperature of water, it has to absorb so much energy in order to do so. So now, what does this mean for the three cities? Cities next to oceans experience moderate, less extreme temperatures because water can absorb heat without changing temperature. Because Vancouver and Gander are located on oceans, the air temperature is moderated by water. Now, I'm going to be kind of general here. Now we're talking about Vancouver and Gander. So let's just go like this. Vancouver on the Pacific Ocean, Gander, Newfoundland. This is kind of just, I don't have to exactly locate these places. The point I'm trying to make is you can see they're both clearly surrounded or very, very close to bodies of water. So let me start there again. Because Vancouver and Gander are located on oceans, the air temperature is moderated by the water. That means they will see less variation in their climate from month to month. Vancouver is located next to a warm ocean current coming from the equator, so I'll draw that for you. So here is a warm current coming from the equator. So we essentially know that this is going to be warm water. I'll put warm H2O. Gander is located next to a cool ocean current coming from the Arctic. So maybe what I'll do is I'll change to blue if I can do that. So that's going to be traveling this way. So this is going to be cool water, or I guess I could put even cold water, cold H2O. This explains why Vancouver has a warmer average temperature. So there you go. So you can see the impact of water on climate. That water is holding a greater amount of energy. And as that water moves by Vancouver, or I guess we could just talk in generality, BC, that warmer water is going to warm the surrounding air, and that's going to influence the temperature. Whereas if you look over at Newfoundland or on the Atlantic side of Canada, that water is going to be cooler. It's going to have less energy. Therefore, what's going to happen, it's going to cool the temperature in the eastern Canada. Okay, so water really seems to dictate the amount of energy in the air. And as you know from science, energy always transfers from hot to cold. So on the BC situation, what's happening is the water is going to hold energy, which is going to be transferred to the air. The air is warmed, goes over Vancouver, warms it up. Whereas what's going to happen on eastern Canada, Newfoundland, the air is actually going to be warmer than the water. What does that mean? The energy is going to leave the air and go into the water, which makes the temperature much lower. Okay. Now, let's look at Lethbridge. So Lethbridge, I'll just kind of go here. You're going to be in Alberta, okay? Because Lethbridge is landlocked, it does not benefit from the regulating effect of the ocean and therefore experiences greater temperature variation from month to month. So let's be clear here. I want you all to remember that if we consider the air, so now I'll just kind of go back, I'll go orange, okay? I really want to reemphasize this. If we pretend these three cities are all right here, we have all acknowledged that the air traveling over, coming from the equator, should be about the same, okay? So the general temperature or amount of energy in the air should be the same. Now, yet Vancouver is hotter. Over in Gander, it's colder. Now, why is Lethbridge all over the place? Why can it be hot? Why can it be cold? Well, that's because in Alberta there, you don't have that big body of water. That means the water is not stealing energy or providing energy. Lethbridge simply is going to rely on the energy or the lack of energy that's in the air. And that's why Lethbridge can be hot in the summer or it can be very, very cold in the winter. So what this proves is that water really does have an impact on the temperature experienced by a city. And remember, water either has the ability to accept energy or donate energy, and we go from there. Now, what we want to do sometimes is we want to measure the amount of energy inside of water. The quantity of thermal energy, that variable, and I'll show you the formula, is a capital Q, is the amount of thermal energy measured in joules that is absorbed or released when the temperature of a substance changes. It is affected by the mass of the substance, measured in grams, the amount of change in temperature, and how easily the substance changes temperature, as indicated by its specific heat capacity. Now, much of this, you're going, well, what are you talking about? What I'm trying to say to you here is I'm going to give you a formula with some calculations, and what's going to happen is we are going to measure how much energy water gains or loses when it changes temperature, okay? Now, this is very important because we just saw the impact of what water can do to temperature, and now we're going to quantify, we're going to measure what happens. We're going to measure the change in temperature. Sorry, let me try that again. We're going to measure the change in energy when water heats up or cools down. So here you go. Here's a formula for you. It is Q equals MC delta T. And yes, I am going to show you some sample calculations. Capital Q is a quantity of thermal energy, that's in joules, a capital J. M is the mass of the substance in grams. C is the specific heat capacity of the substance in joules per grams times degrees Celsius. We'll get to that. And triangle T means change in temperature. Now, I said to you we come to specific heat capacity. The specific heat capacity of water is 4.19 joules per grams times degrees Celsius. Now let me try to break that down. This means that it takes 4.19 joules of energy to warm 1 gram of water by 1 degree Celsius. Now, for you and me saying, okay, well, that's 4.19 joules. Well, is that a lot or a little? We don't really know until we compare it. This number is very high compared to other substances. For instance, aluminum, 0.9, copper, 0.38, and lead is 0.130. Which means, compared to these metals, it takes a lot more energy to make water change temperature. Or put it another way, water can absorb a lot more energy without changing temperature. So there you go. So water has a specific heat capacity of 4.19 joules per grams times degrees Celsius, which basically means if you had 1 gram of water and you want it to go up 1 degree Celsius, which is not very much, you need 4.19 joules of energy. And if you compare it to other metals, that's a heck of a lot. Now, this 4.19 joules is going to be our specific heat capacity for water, and that's going to be our C value in that formula, Q equals MC delta T. Oh, I hit forward. There we go. Now, how the heck, what are we talking about here? Now, how do we measure this temperature change? Finding the specific heat capacity. The C of other substances can be determined using a calorimeter. A calorimeter is a container that is insulated to avoid heat loss. When I was in school, we used this right here. It was made of 2 styrofoam cups. To determine the value of C for another substance, it is mass, placed in a calorimeter and heated. So what I'm going to say to you here is this, okay? I don't want you to really get into the details, but I am going to explain to you what's happening. You see, maybe if I was with you in a class, we would try to do a lab on this. What we do, I'll keep it very simple. I want you to pretend that we have a block of hot copper. Okay, so here's copper. And this copper has been, it's been in a fire or in an oven, and it's really been heated up, okay? So it's very, very hot. And someone says to you, hey, how much thermal energy is in that copper? Well, I have no way of knowing. What we're talking about here, and this is something I'll come to you in Chemistry 30, is you can use a calorimeter here like the one on the right. And what happens is it's a very insulated system, which means it doesn't really lose too much energy. And I'm keeping it very brief. I'm doing a very quick job. So what we do is we fill it with water. And here's what would happen. At the very beginning, I would measure the temperature of the water, okay, with a thermometer. And I would record that. Then what I would do is I would place that hot metal inside of the water. Whoops, change back to orange. Now what's going to happen is that hot metal has more energy than the water. And what happens is that energy will be given off and transferred into the water itself. And what I'm trying to say to you here is this is a way of finding out how much energy the metal had. And here's what I mean. Through these calculations, this Q equals MC delta T, I can figure out how much energy the water gained. So again, I'm keeping this very brief, but let's say I use this formula, Q equals MC delta T. And let's just pretend I figure out the water has, let's say, 2,000 joules of energy. That's how much it gained. And again, I'm not making you do the experiment, just bear with me. You see, if I did this with you, we would determine that the water gained 2,000 joules of energy. Well, where did that energy come from? The energy must have come from the copper. That's how much it lost. And all I want you to know here basically is a calorimeter, this experiment, is a way of determining how much energy something has. And it's kind of an indirect measurement. So what you do, to recap, is you take that hot metal, you put it inside the water. And what we can measure is the fact that the temperature of the water went up. And by using this Q equals MC delta T, I can determine that the energy of the water went up some amount. In this case, I used 2,000 joules. Well, if I was doing the lab with you in person, we'd have to determine, well, if the water went up 2,000 joules, well, where did that 2,000 joules come from? It must have come from the metal copper. Therefore, we know that the metal copper had 2,000 joules of energy. Okay, so I don't want you to get hung up on this too much. I just want you to be kind of introduced to the idea of a calorimeter. It will come back to you in Chemistry 30. But what I do want you to focus on though now are some of the calculations. Okay, here we go. So what we want to do, it says here, you have 50 grams of water at 25 degrees Celsius, and it is heated to 50 degrees Celsius on a hot plate. Given that the theoretical specific heat capacity of water is 4.19 joules per gram times degrees Celsius, determine the value for Q. So now, you have to think first of all, look at the temperature of the water. The water went up by 25 degrees. It went from 25 to 50. So in this case, have we gained energy or have we lost? If the water is going up in temperature, it must be gaining energy. Let me show you now how this is done. And by the way, if you've done the chemistry and physics unit, this will be a lot easier. Step 1, you always write your blank formula. Q equals MC delta T. Step 2, you input your values with units. You must have units. So you're going to go Q equals 50.0 grams. Now, C is your theoretical heat capacity of water, 4.19 joules per grams times degrees Celsius. And let's see here, what was our change in temperature? We went from 25 to 50, so that is positive 25 degrees Celsius. What you're going to do is you're going to multiply those together. So what I'm going to do, I'm just going to use my phone here as a calculator. So we're going to go 50 times 4.19 times 25. And what that will give you is an answer of 5237.50 joules. Now, that's the right answer, but remember, from chemistry and physics, you must use significant digits. And in the question, you can see that we have 3 significant digits. Now, what I'm going to say here is I have covered significant digits in chemistry and physics. If by chance you're doing this video first or this unit first, I'm going to ask that you ask your teacher to allow you to look at either chemistry or physics for you to determine how to write significant digits and scientific notation. Well, to show you how that's done really quick here, like I don't really want to go over it again, but we have to have 3 digits. So we're going to take the 5.2, this 7 will round you to a 4. So it's going to be 5, 2, 4. And our decimal is going to jump once, twice, 3 times. 5.24 times 10 to the 3 joules. Again, I'm not trying to be rude or a bad teacher, but in chemistry and physics, we have gone over significant digits. As this is Unit 4, I'm really hoping that you have that down by now. Oh, and by the way, that's how you would get 100% on this question. Blank formula, input with units, and a final answer with units and sig digs. Here we go. How much thermal energy must be released to decrease the temperature of water by 10 degrees Celsius? So, step 1, Q equals mc delta T. So what do we have here? We want to figure out our energy. Do we have mass? Now, remember, our mass must always be in grams. To go from kilograms to grams, you want to times by 1,000. So 1 times 1,000 should be 1,000 grams. The specific heat capacity of water is not going to change unless we're told. 4.19 joules per gram times degrees Celsius. Now, there's a couple ways this could be done, but I really want you to focus on this here. The temperature decreased by 10 degrees. You see, in the last example, it went up 25 degrees, so I put plus 25. This time, we're going down, so what I'm going to do is I'm going to put minus 10.0 degrees Celsius, because we've gone down in temperature. Please be aware of that kind of sign notation. Okay, I'll multiply this out here, so we have 1,000 times 4.19 times 10, which is minus. You're going to get negative 41,900 joules, which is just about the right answer. But again, we want to have significant digits. So if you look, your decimal right now is sitting after that 0. We can only take 3 digits along for the ride. 2, 3, 4. You always move it there in between the first and the second number. So really, it's going to be minus 4.19 times 10 to the 4 joules. In other words, the water must have lost or given away 4.19 times 10 to the 4 joules, and that does make sense since the temperature did go down. Okay, now what I've done here is, I'm just going to do this really, really quick. I've given you some practice questions here, so 1, 2, and 3, and what I'll do is I'll just answer them here on the next few slides. So here we have 200 grams of water at 4 degrees Celsius. It's warm to 22 degrees Celsius. So again, you're probably finding this repetitive just about. Q equals mc delta T. Number 2, see, they want the amount of thermal energy. Oh, and it's absorbed. That means it's taken energy in. That also means we should go up in temperature, right? We have 200 grams Specific heat capacity is 4.19 joules per gram times degrees Celsius. Oh, sorry. And we went up there. How many degrees is that? That should be 18. So positive 18 degrees Celsius. Step 3, Q. Let's multiply this out. 200 times 4.19. Whoa. 200 times 4.19 times, I think I'm getting my calculator messed up. 200 times 4.19 times 18. I got 15,084 joules. It's positive because you're going up. We'll put that into significant digits, which is 3 again. So that 8 will round up there. So it should be 1.51 times 10 to the decimals right there. 1, 2, 3, 4 joules. There's that one done for you. Do another one. We want, again, to determine the quantity of energy required. So step 1, Q equals MC delta T. Step 2, put in your values. Now it does say here we have 1 kilogram. Remember, kilograms you always got to put into grams. You times it by 1,000, so that should be 1,000 grams. Although be careful here, it did say this time we're using a different heat capacity. So that'd be 2.00 times 10, or sorry, 2.00 joules per grams times degrees Celsius. Now, if you look, our temperature, we went from minus 15 to 0. That still is a gain of 15 degrees Celsius. Multiply it together, and that should give you, so I'll clear that out, 1,000 times 2 times 15, which is 30,000 joules. And based on, oh, look at this one. We'll go with 2 significant digits. So that would be, so we're going to move right here. 1, 2, 3, 4. 1, 2, 3, 4. 3.0 times 10 to the 1, 2, 3, 4 joules. Again, I'm flying through significant digits in scientific notation because we have covered that in chemistry and physics. Please speak to your teacher if you need a review on that or access to my videos. Last one here. Oh, good. This one now is a little bit of algebra. Step 1, Q equals MC delta T. Now look, what's different? This time, they want you to figure out the heat capacity, which means we must have everything else. This time, look at that. 21.6 joules of energy are used to heat iron. So that means our Q value is 21.6 joules. Our mass is 2.0 grams. We're going to solve for C, and we have raised the temperature of the iron by 24.0 degrees Celsius. Now, again, I haven't taught you math. Depends how you want to do this. I'll kind of show you my way. What I would do here, everyone, is I'd go 21.6 joules. I would multiply these two numbers together, and that's going to give you a value of 48 multiplied by C. Because you see, this is all multiplication here, so I'm going to multiply these two numbers together and leave the C alone. Now, according to algebra and the rules, you need to get C by itself. 48 and C are being multiplied by each other. How do you undo multiply in algebra? You divide. You divide this side by 48, but that also means you have to divide the other side by 48. And that's going to give me a value. So I'm going to go 21.6 divided by 48. It gives me an answer of 0.45. Now with significant digits, oh, actually that's good. Look, that's 2 sig digs right there. And this is in 2 significant digits already. Our units for specific heat capacity never change. That's going to be joules per grams times degrees Celsius. Done. That's a good one to know. A little bit of algebra. Okay, moving along to our last section here. The hydrologic cycle and energy transfer. We've seen how liquid water is able to absorb, release thermal energy and its effects on climate. We have definitely seen that, and we've also seen how much energy it takes to raise or lower the temperature of water. I mean, that's what the whole point of Q equals MC delta T is. You can really see that if you want water to go up in temperature, you need a great deal of energy. Vice versa, if water cools off, it releases a great deal of energy. Just imagine Vancouver or Gander over in Newfoundland, which is surrounded by all this water, whether it's taking in energy or giving off energy, the impact that must have on the climate. That's the whole purpose here, is to bring it full circle. Now, the hydrologic cycle is the movement of water molecules throughout the biosphere. Besides the movement of liquid water in convection currents, water in the cycle also changes from solid to liquid to gas, and vice versa. Sorry, I don't know why that didn't come through. That's the word "to" right there. We know about this. Water changes states, doesn't it? Solid, liquid, gas. Of course it is, based on the temperature. We know about if water is below 0, it should be frozen. Between 0 and 100, it should be liquid. Above 100, it should turn into gas form. We know this. Phase changes. Oh, this is what I'm talking about. During a phase change, water changes state without changing temperature. This occurs because thermal energy is going towards breaking the bonds between the water molecules, rather than making the water molecules move faster. So you see, if you look at this table, this is very important. I'm going to give you some temperature. You might want to put this in. If you look right here, look at this. This is all about water, by the way. It's only water. This is going to be 0 degrees Celsius. Below 0 degrees Celsius, you should be frozen. Then something happens at 0 degrees. Right? That's the change between solid and liquid. As you go up, something happens at 100 degrees Celsius. That's where you change from a liquid to a gas. See, what we're focusing on in this part, everyone, now, is we're focusing right here. We're going to be doing some calculations right about, or focused on, when water changes states of matter. Again, right here. This occurs because thermal energy is going towards breaking the bonds between water molecules, rather than making the molecules move faster. So you have to now understand that when water changes states, there is energy involved. We're not talking about changing temperature. We're just talking about when you hit that magical number, let's say of 0 degrees Celsius, energy is being, added or subtracted because we have a change of state. So what I want you to understand is whenever we have a change of state in regards to water, there is energy coming or going. Okay. Let's see here, probably some more explanation. Since water molecules undergo many phase changes in the cycle, a lot of energy is transferred in the biosphere without any change in temperature. This helps to keep average global temperatures relatively stable. That makes sense. You have to think of it. On any given day, just think of water going through the cycle. My goodness, the amount of water that evaporates or falls back down as precipitation. Water really is going through a lot of phase changes throughout the day across the planet. That is a lot of energy added and subtracted. Now, the heat of fusion. The heat of fusion of a substance is the amount of energy absorbed when 1 mole of the substance melts from solid to liquid without changing temperature. Very interesting. It is equal to the heat of solidification, which is the amount of heat released. Okay, what are we talking about here? Let me make this very, very clear. Heat of fusion. Okay, let's make this really clear. Let's break this down. It is the amount of energy absorbed. So think of it. If you have ice and you want to go to liquid water, let's go liquid water. Think of it. Are you absorbing or losing energy? Well, we all think of ice, as being the colder version or the below 0 version. You see, as you get, if you want, you have to gain energy here. You have to go from the ice version, the solid, to the liquid version. So it's going to absorb energy. And what they consider it's 1 mole. Now again, I don't want to go over that too much because I explained what a mole was in the chemistry unit. Furthermore, this amount would be the exact same as if you had liquid water cooling off and changing states to ice. Now again, this is not generally about a change in temperature, but you have to understand, in general, if you have a body of water and it's cooling off, it has to go from the liquid stage into the ice phase. If you have water heating up or ice, it has to go from ice, change states, to liquid water. The point is, there's this heat of fusion. Whenever you want that change between ice to liquid or liquid to ice, it's the same amount of water. So heat of fusion is this change, this state, phase change right there. Heat of vaporization, which you probably guessed, is this one. That is the energy when we are going between liquid and gas. Okay, so you have to think of that. Heat of vaporization is the amount of energy either absorbed or given off when we have the phase change between liquid and gas. Okay, so again, everyone, this is happening, vaporization is happening at 100 degrees Celsius. I guess if I go back here, heat of fusion is happening at what temperature? 0 degrees. We are just talking about the energy of the phase change. Fusion is when you go between the ice and the water in that area right here. Vaporization is this one right here. Okay, now, just like I told you, remember the C value for water is 4.19 joules per gram times degrees Celsius? Well, there are 2 numbers you need to know here as well. The theoretical heat of fusion is 6.0 kilojoules per mole. That goes right here. And don't worry, I am going to show you calculations. Kilojoules per mole. And for your heat of vaporization, let's go with 40.7 kilojoules per mole. That's what's going to be on your formula sheet. Okay, I'm going to show you down the calculations. Remember, we are just trying to determine the amount of energy that is either being absorbed or lost when we are undergoing a phase change, okay? That's all we're doing. So what you have to do here, it says calculate the amount of energy absorbed when 10 moles of ice at 0 degrees melts. The theoretical heat of fusion of water is 6.01 kilojoules per mole. So here is your formula, everyone. Heat of fusion is equal to Q over N. Really easy. You see this 6.01? That's your H of fusion. Nice and easy. Just put that value right there. Kilojoules per mole. Okay? Now, calculate the amount of energy. Energy is your Q. It's always your Q. Put it right there. Now, how many moles do we have? N is moles. Well, in the question they tell you, you have 10.0 moles. Now again, I haven't taught you math, so I'm going to kind of go with the algebra that I would use. You need to get Q by itself. What is happening to Q? It's being divided by 10. Well, how do you undo divide by 10? You multiply by 10 on this side, which cancels it out. But if you do it on that side, you better do it on this side here as well. Okay, I will multiply that together, and that would be 6.01 times 10, which would give you 60.1. Okay, 60.1, hold on here, should be kilojoules. Now the only thing I want you to notice here is if you look at your units, in this case, your Q value is in kilojoules. Just be aware of that here, okay? And that does make sense. If you look at the units, the H of fusion was in kilojoules. So just so you know right here, in these phase change questions, we are looking at energy in kilojoules, whereas in the Q equals mc delta T, it did seem that we were dealing more with joules. Again, very easy calculation. Now, I don't want to go into this too much because if you've done chemistry, you should know how to calculate moles. Because again, this formula is H of fusion equals Q over N. And what's going to happen in some cases, they're not going to give you the N even though you need it. So I guess what you need to have in front of you is a periodic table. And if you don't have one anymore, you're going to have to ask your teacher. Anyway, I'll show you here what I mean. So we want to determine the experimental heat of vaporization. So here, your formula is going to be HVAP, or that's going to be the heat of vaporization. And that's going to be Q over N. Now they want us to figure out this value. Okay, let's go. So HVAP. Now Q, do we have a Q value in here? It is found that when 150 grams of water evaporates, 339 kilojoules of energy is absorbed, taken in. That's positive. So 339 kilojoules, that's your Q value. Now, do they give us moles in the question? No, they don't, everyone. You have to figure this out. Now, this is a review from the chemistry unit. In the chemistry unit, what I had gone over, and I'll make it kind of brief, and it was on the last slide. If you want to determine moles, that is mass divided by molar mass. So if you read the question, your mass is 150 grams. And in this case, they do tell you the molar mass. It says right here, recall the molar mass of water is 18.02. So you get lucky in this one. So what you have to do here, everyone, is you have to figure this out first and then put it right there. So I'll use my phone here again to figure out this value. 150 divided by 18.02. Now it's a big long number. I hope you're trying this. It's 8.32 ... moles. It goes on forever. What I would suggest is just kind of leaving that in your calculator. But anyway, so you're going to go, so then you come over here. This is going to be that 8.32 number. And all you have to do now is divide. So your HVAP is going to be 339 divided by your number of moles, which was that 8.32 number. And give or take, you're going to get a big long, but if you have to use significant digits, we need to have 3. I get 40.7. Now remember, what should that be? Look at your units, kilojoules per mole. So kilojoules per mole. There's your answer. Okay? Let's move along. Okay, so these are going to be 2 practice problems that I'll solve for you right now. So here you go. You have when 8.70 kilojoules of thermal energy is added to 2.50 moles of liquid methanol, it vaporizes. Determine the heat of vaporization. Step 1, HVAP is Q over N. Step 2, let's put in some values. Now remember, the energy is always your Q value. So we have 8.70 kilojoules divided by, oh, we have moles. 2.50 moles. Step 3, HVAP. Let's divide. Get out my phone here again. 8.70 divided by 2.50. I get 3.48, look at your units, kilojoules divided by moles. And is that, yes, that is the right number of significant digits. There are 3 there and 3 there. There's your final answer. Last one. If the theoretical heat of fusion of ice is 6.01 kilojoules per mole, how much thermal energy is required to melt a 100-gram ice cube? Okay, step 1, so H of fusion is Q over N. Remember, it's fusion, that's why I put FUS right there, fusion. Step 2, So look at this. They have given us the heat of fusion is 6.01. So this is going to be 6.01 kilojoules per mole. Now, how much thermal energy? That's always your Q value. And we need our moles. And you see, wait a minute, it doesn't tell you moles again. Well, you're going to have to do that side calculation. N moles is mass divided by molar mass. That's going to be 100 grams. Now, even though we've done this in the past, you see the molar mass was not given to you here, and I'm just going to tell you, this is really important. Some of your questions will not tell you the formula. So you're going to have to look it up. It's going to be in your periodic table. You have to look things up. In this case, we know the formula for water is H2O. You have 2 hydrogens and 1 oxygen. So what you have to do is you actually have to look at your periodic table. You see the mass, okay? So you should have your Chem 30 data booklet in front of you, and that will have the different masses, okay? So what you're looking at here right now, pardon me, sorry, is you want to find the atomic molar mass of hydrogen and oxygen. Now you see, you have 2 hydrogens. So if you find hydrogen, that is 1.01, but we have 2 of them. So 1.01 plus 1.01. Now what is oxygen? Oxygen is 16. We only have 1 of them, 2 of those. So if you add that all up, that gives you a molar mass of 18.02 grams per mole. If you divide that now, you'll get your number of moles. So you're going to go 100 divided by 18.02. That will be 5.55 moles. Let's go like that. I'm kind of abbreviating. That value's got to go over here. So you have 6.01 kilojoules per mole. Q over 5.55 moles. Now, like I said before, Q is being divided by that 5.55. So to undo that, we're going to multiply. So 6.01 times 5.55 gives me an answer. I'm going to go quickly here into the significant digits. I get 33.4. And remember, in these type of questions, our Q value is in kilojoules. Now, let's not kid ourselves. This is a long video with a lot to know. Do you have to know how to do these calculations? The answer is yes. If we were in a regular classroom, I would teach this over a very long period of time. So I get it. I'm with you. There's a lot going on here. Please rewatch. Please watch in sections. And please make sure you can do the calculations because you know they're coming at you on the quiz and the exam. Very important, okay? Try the practice questions. Get your hands on a periodic table. And best of luck.